This video is about chapter 21, and in this chapter we will discuss a variety of topics related to hypothesis tests and confidence intervals. You've already had these explained to you, you've done some examples with them, so now you're ready to see how they're related to each other and to understand hypothesis tests at a deeper level. Now, I will tell you up front that some of these ideas are a little bit abstract. Okay, so don't rush through these ideas. Make sure you take your time and maybe rewatch this video a second time if that would help you. Okay, by the end of this video, you should be able to clearly explain what a p-value is. You should also be able to define these words: alpha level, type 1 error, type 2 error, power, and effect size. There's lots of vocabulary in this chapter. You should also remember when to reject the null hypothesis and when to fail to reject it. You should also be able to explain how confidence levels and significance levels are related, and explain how alpha, beta, and power are related. So, the first thing is reviewing briefly what the null hypothesis is. It's very important that you have a very clear idea of what the null hypothesis is. Okay, so here's some important reminders about the null hypothesis. The value for the null hypothesis comes from the context or situation, not from the data. In fact, you should make your null hypothesis before you collect any data. Okay, and most commonly, it's based on there being no change from the past. Okay, the past history is it's been this. We've made some kind of a change, and we're seeing if the parameter has changed. Okay, also very important, you can never prove that the null hypothesis is true. We can only reject it or fail to reject it. You should never say the words "except the null hypothesis." Next, let's remind you about the p-value. The p-value is not the probability that the null hypothesis is true. It's also not the probability that the null hypothesis is true given the data that you collected. The p-value is the probability of getting results at least as unusual as the observed statistic given that the null hypothesis is true. Okay, keep in mind that the p-value is a conditional probability. Given that the null hypothesis is true, how unlikely is it that I got the results that I saw from my data? Okay, that leads us into the idea of the alpha level. Sometimes we need to make a firm decision whether or not to reject the null hypothesis. Okay, when the p-value is small, it tells us that our data is rare given that the null hypothesis is true. So the null hypothesis is probably not true. Okay, but how small exactly is a small enough p-value to be okay? Okay, we will decide this before we collect any of our data. Okay, and now it is an arbitrary value, but this arbitrary threshold for our p-value is called the alpha level. Okay, it's also called the significance level because when our p-value is below this threshold, we say our results are statistically significant and we reject the null hypothesis. Okay, common alpha levels are 0.1, 0.05, and 0.01. Okay, we'll kind of stick to those values. The most common one that you'll see is the one in the middle, 0.05. Okay, if it's not that important of a topic of a test, you may be okay with moving it to 0.1. If it's very important that you have it correct, meaning medical procedures and things tend to be more, have a lower alpha level of 0.01. And we'll talk later on about the advantages and disadvantages of having a higher and lower alpha level. Okay, a reminder that when the p-value is below the alpha level, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. Okay, now to help you remember this, okay, I found this online, I think it's read, when the p-value is low, reject that null hypothesis. When the p-value is high, let it fly. I think that's how you read it, but I could be wrong. Okay, let's talk about the relationship between confidence intervals and hypothesis tests. There are many similarities between confidence intervals and hypothesis tests. For example, they are built on similar calculations and come up with similar results. Okay, so for example, a hypothesized proportion not being in the confidence interval is similar to a hypothesis test where you reject the null hypothesis. Okay, so down here I have my hypothesized, my null hypothesis value, and p hat comes from our data. Okay, and then here's the confidence interval around our observed statistic. Okay, so the p if p naught is not in the confidence interval, that's the same as rejecting the null hypothesis. However, if p naught is in the confidence interval, that would be similar to failing to reject the null hypothesis because that p naught value is a reasonable value based on the data that you saw. However, the confidence level can be 90% or 95% or 99% or some other confidence level. And the significance level can be, or the alpha level, can be 0.1, 0.05, 0.01, or any other level. So we can ask ourselves, is there some kind of relationship between confidence levels and significance levels? And the answer is yes. A one-sided hypothesis test where the p is less than some hypothesized value or p is greater than some hypothesized value is the same as alpha equaling 100 minus the confidence level. Okay, so for example, if alpha is 0.05, that's the same as a confidence level of 95. Okay, or a alpha level of 0.01 is the same as a confidence level of 99% confidence level. Okay, that's a pretty simple relationship. A two-sided hypothesis test is a little bit trickier because you have the extra side to deal with, and that's the same as the alpha level of 0.05 times 100 minus the confidence level. So if the confidence level is a 95% confidence level, then that would be the same as alpha equaling 0.025. Okay, or if the confidence level is a 90% confidence level, okay, that would be the same as having an alpha level of 0.05. Okay, so there's some equations you can use to figure out the relationship between alpha and the confidence level. I would say that these are more likely to show up on the AP exam than the one-sided because it's a little trickier. Okay, type 1 and type 2 errors. Now that we have decided an exact threshold, a level at which we will either reject or fail to reject the null hypothesis, we must acknowledge the fact that we will make some mistakes. Okay, and there are exactly two ways to make an error in a hypothesis test. A type 1 error is where the null hypothesis is true and we reject it. Okay, a type 2 error is where the null hypothesis is false and we fail to reject it. Okay, now I've kind of developed the acronym when the null hypothesis is true, you reject it, which kind of looks like hotter. And so I remember that type 1 is hotter than type 2. Okay, that a type 1 error is when the null hypothesis is true and you reject it, which by deduction means the type 2 error is when the null hypothesis is false and we fail to reject it. Okay, so the question is, how often will a type 1 error occur? Well, it occurs when the null hypothesis is true and we reject it, which happens when the p-value is below alpha, which means that a type 1 error will occur with the probability of alpha. When we set our alpha level, we're also setting the probability that we'll make a type 1 error. Okay? Now we can talk about the probability of making a type 2 error, but it's a little more difficult to determine the probability of making a type 2 error because we don't know what the true value of the parameter is. And so it's a little more abstract there. But just for notation and kind of thinking it through, we will call that probability beta, type 2 error. The probability of making a type 2 error is beta. Now, the next idea is kind of related to type 1 and type 2 errors. It is the idea of the power of a test. Now, remember that we can't prove a null hypothesis true. We can only fail to reject it. Okay? And if we're trying to reject it and we fail to reject it, we may kind of assume that, well, it must be true then. But sometimes we wonder if we've looked hard enough, meaning it is possible that the null hypothesis is false, but we didn't collect enough data, and so we kind of are left with assuming that it might be true when it really is false and we didn't look hard enough. Okay? The power of a test is the probability that it correctly rejects a false null hypothesis. Okay? Now keep in mind that a type 1 error is hotter than type 2, and so if the null hypothesis is false, then we can only make a type 2 error. Okay? If the null hypothesis is false, then it's not hot in that acronym. Okay? It's a type 2 error, which is beta. Okay? So the power of the test would then be equal to 1 minus beta, which we can't, actually calculate. But we can talk about things that will increase and decrease the power using this equation. Okay, before we get into talking about how power and beta and alpha are related, I want to bring up one more idea, which is the idea of the effect size. The effect size is the distance or the difference between the null hypothesized value, P naught, and the true proportion. Okay? If there's a large effect size, meaning that the true proportion is, let's say, 0.5, but for some reason you think it's 0.3, then if there's a large difference between those values, it will be much easier for you to correctly reject that null hypothesis, because all your data will be somewhere around the true proportion, not your hypothesized value. Okay? So if the effect size is large, then the power will be high. Okay? Now here's some other things that can either increase or decrease the alpha level. Okay? Now, again, alpha level is a type 1 error, which is written type I, and type beta is a type 2 error, which is written II. Okay, and the power is 1 minus beta. Okay, so if you say I want to, I don't want to make a type 1 error, and so I'm going to decrease alpha. Okay, have a very low alpha level, an alpha level of 0.01. What that will result in is you'll be more likely to make a type 2 error. It'll increase beta. Okay, now the power is 1 minus beta, so if you increase beta, what you're really doing is also you're decreasing the power. Okay? Now if you say, well, I don't want to do that, I want to increase the power. So let's increase alpha. Let's have alpha be 0.1, a higher alpha level. What that will result in is a lower chance of making a type 2 error. It would decrease beta, but it would increase the power. Okay? So notice that as long as your sample size is the same, that alpha and beta have these inverse relationships, and notice that the power will be the same as alpha. Okay, so as long as the sample size is the same, then decreasing the alpha level will decrease the power, and increasing the alpha level will increase the power. Okay, now what happens if you change the sample size? Okay, and the most common thing is if you increase the sample size, okay, if you collect more data, what will happen is you will decrease your chance of making a type 1 error because you have more data. You will decrease the chance of making a type 2 error because you have more data. And because beta and power are inversely related, you will then increase your power. Okay, so if increasing your sample size, getting more data, will lower your chances of making errors and increase the power of your test. All those are good things. Okay, so that's the end of this video. I know there were lots of different topics. Some of them were clear or not clear. Please bring questions to class, but hopefully you better understand what a p-value is, what an alpha level or a significance level is, a type 1 and a type 2 error, the power and effect size. Hopefully now it's clear when to reject the null hypothesis and when to fail to reject it. That has to do with the p-value being lower than alpha or above alpha. Okay, you should be able to know how confidence levels and significance levels are related, and also how alpha, beta, and power are related. Okay, thank you so much for watching.